So today's speaker is David Radice. He did his master's degree in Milan, and then he went to the Max Planck Institute for Gravitational Physics in Germany, where he did his PhD. And now he's a Walter Berg Fellow for Theoretical Astrophysics and Relativity at Caltech. And he will talk today about double neutron star mergers. Yeah, please proceed.
Okay, thank you very much for the introduction, and thank you for giving me a chance to talk about my work at this online seminar series. Today I'm going to talk about double neutron star mergers. This is a very big topic. I will not be able to cover everything, so I will focus only on those aspects that are closer to my work. And I should mention, of course, that this work is work that has been done in collaboration with many people that are listed here. So let me start with, if I manage, with a brief summary. So I will start with a brief introduction. What are bineutron stars? This is something just to get everybody on the same page. Then what I'm going to do is I'm going to focus on one particular binary, or one typical binary, as it inspirals and merge, and we're going to look at it through his history. So first I will talk about the late inspiral and about the kind of science that we can do by observing late inspiral and merger signals from merging neutron stars. Then I'm going to switch topic a little bit and talk about post-merger evolution. And finally, the nuclear-rich outflow that can come from these mergers. So let's start with a little bit of background. What are binary neutron stars? Well, binary neutron stars are a binary system composed of two neutron stars. We know of a few of them in our galaxy and in globular clusters around our galaxy. And here is a table with all of the known binary pulsars. It has a few interesting numbers like the relative, the masses of the two neutron stars and so on. But I would like you to focus on this particular column, which is the period of the binary in days. So one thing that immediately one can easily recognize is that there are a handful of these binaries that have periods of less than 1 day. So the 1 day period is basically the threshold between binaries that will merge within the Hubble time and binaries that will not merge within the Hubble time. These binaries at a very short period are already very relativistic. They are emitting gravitational waves and their orbit is decaying. And this is, of course, how gravitational waves were first inferred to exist already in the 90s by Tews and Taylor. They measured the evolution of the period for one of these binary pulsars, the 1913 plus 16. And they show that the orbital decay is perfectly consistent with general relativity. Of course, more recently, advanced LIGO directly measured gravitational wave from binary black holes, but this was the first indication of the existence of gravitational waves. So binaries like this binary evolve over hundreds of millions of years as the orbits shrink until the point where they really reach the sensitivity band of ground-based detectors such as advanced LIGO. This happens basically when the binary have an orbital frequency of around 5 Hertz. The gravitational wave frequency at that point is twice the orbital frequency, so it's 10 Hertz, and this is where LIGO starts to become sensitive. And here is an example of a plot showing the trajectory that the binary does in the sensitivity band of a gravitational wave detector. You can see here a number of lines, like this one on the bottom for Einstein telescope. This one dashed line is for advanced LIGO. These are basically the sensitivity curves of gravitational wave detectors at their design sensitivity. Signals, you can think that signals that are above this sensitivity threshold are detectable, and signals that are below are undetectable. Of course, it's more complicated than that. So what a binary does is it will appear in the gravitational wave band at low frequency and then move in frequency as the orbit decays. So when the orbit decays, the gravitational wave emission becomes more and more efficient. So the amplitude goes up, but the binary spends less and less time in each frequency bin. So at the end, you can work out an effective spectrum, which is just a simple power law at low frequency that shows how the gravitational wave signal evolves. So it moves from high frequency to low frequency with a characteristic slope. And then when it reaches sufficiently high frequency, we think at around 300 hertz or so, tidal effects and other high order post-Newtonian terms start to become important, and the dynamics start to become complicated and can no longer be described by just simple analytic predictions like this power law. And from this point on, the last, say, 10 or 20 milliseconds of evolution can only be simulated with numerical relativity, so by doing fully nonlinear simulations. So one of the main aims in these simulations is trying to understand, first of all, how the binary evolves towards the merger, and secondly, also to construct full gravitational wave signals by matching together analytic predictions at low frequencies with numerical predictions at high frequencies, in order to be able to have robust theoretical predictions of what binary should do from the point of view of gravitational waves. I will come back later and explain why we think that this is something worth doing, extracting gravitational wave signals from binary stars. Let me just have one slide on the main tool that I use for my research. This is a code that I wrote during my graduate studies when I was at AEI. It's called Whisky THC. And all of the simulations that I'm going to present today have been performed using this code. This is a code that has generative easy gravity. So we evolved the Einstein equation using the BSSN formalism. It solves the equation for relativistic hydrodynamics, including support for tabulated composition and temperature-dependent nuclear equation of state. And it has a simplified treatment for weak interactions, neutrino cooling and absorption of neutrinos, using a simplified prescription, the leakage scheme. If you're wondering about the name, THC stands for Templated Hydrodynamics Code, and templated stands for the fact that I use programming technique called template metaprogramming. So this allows this code to be very flexible. I can easily plug in different numerical schemes or different physics ingredients and do simulations very quickly. And here is an example of one of the merger simulations we are performing. This is a 3D volume rendering that a student in Frankfurt, Cosima Abreu, recently rendered. You will see the density of two equal mass, 1.4 solar mass neutron stars that we evolved with the Latimer-Sweast equation of state from an initial separation of 45 kilometers. So you see, as the simulation starts, the two neutron stars start to orbit each other. They're losing gravitational waves, so they're emitting gravitational waves. The orbital period accelerates. Eventually, the two neutron stars touch, and the dynamics becomes very complicated. Some matter gets ejected at very large velocities. You form a thick accretion torus, and the remnant that stays supported against collapse for a few milliseconds by the large amount of rotation. And eventually, you form a black hole. You can see here this white sphere denotes the position of the apparent horizon that we find in our simulation, surrounded by a thick accretion torus. So this is this kind of evolution is basically generic for binary star mergers. There are, of course, differences depending on the initial models and the equation of state that you choose, but this is a very generic picture. So now that we have an idea of how binaries evolve, I will focus a little bit, just a couple of slides, on the initial phase of the evolution from the point of view of numerical simulation, which is the late Inspiral, the last 10 to 15 orbits. And in particular, I will focus a bit on tidal effects. So why tidal effects are important and why do we care about this? This, I think, is really well summarized in this plot that I took from this recent paper by the Kyoto group. You can see here a plot which is very similar to the one I showed before. This is plot showing the spectrum of the gravitational wave signal, so how much energy is at each frequency, overlaid with the sensitivity curve of advanced LIGO when it will reach its design sensitivity somewhere in 2019. And you can see here different simulations performed with different equation of state. all of these binaries, they behave basically almost identical until frequencies of about 500 hertz or so. And then they start to depart from each other. What is happening here? Well, what happens is that neutron stars have a finite radii, and part of the energy that's in the orbit is actually transferred to the tidal deformation of the two stars. So the stars become tidally deformed. They emit gravitational wave as a consequence of their tidal deformation. So they radiate angular momentum faster. As a consequence, large neutron stars evolve faster through the frequency range of the detector, and the spectrum becomes lower. And you can compare this, for example, with this dotted line, which is binary black holes. Binary black holes have no tidal deformability. Neutron stars have tides, so they evolve faster as they move through the frequency band of the detectors. These differences might look small, but actually, if you plot the gravitational waves and you look at the phase evolution, which is what we measure with advanced LIGO, or what we will measure, these differences are really significant, of the order of several radians in the last few 10 orbits. And this is something that will be measurable. And as an example, I show here this other plot from another paper by Del Pozzo and collaborators, where they did a systematic analysis showing the kind of science that it would be possible to do with advanced LIGO once we have a sufficient number of detection. So what I show here is the estimate for the tidal deformability, is the tidal loft number of the 1.4 solar mass neutron star, which you can take as a particular constraint on the radius of neutron stars. It depends on the leading order on the compactness of the neutron stars, mass and radii, and also it has a weaker dependence still on the equation of state. And they show that even for very short equation of state like the SQM3, with 20 or so detections, we will be able to measure very accurately this tidal deformability. And by stacking together a large number of detections, it will be possible to tell apart many different equations of state and rule out a lot of models. Of course, the catch here is that we need a lot of events. It's going to be unlikely to be able to place strong constraint on the equation of state or neutron star radii if you want from a few loud events, but we really need many. This is one of the outcomes of this study that consider also realistic data analysis techniques. And the other important aspect is we need very accurate theoretical models. All of these analysis can only be performed if we have very good predictions of how the phase evolution in the last few orbits actually behaves and how this depends on the equation of state. And this has been one of the main drivers behind trying to do accurate numerical relativity simulation of neutron star mergers. And here is basically a slide summarizing the current state of the art. So modern numerical relativity codes have become very accurate. We introduced, for example, in 2013, the use of high-order numerical schemes. And now we have reached the point where we can simulate a binary over 10 orbits and have an accuracy of less than 0.1% in the phase evolution, as is shown here in the bottom. Numerical relativity simulation have also become able to simulate very long inspirals, so really breaching the gap between these analytic models at low frequencies and numerical predictions at high frequencies. For example, Roland Haas and collaborators recently published a waveform containing more than 23 orbits, which was something unthinkable even 1 year ago. And finally, the community has started to develop very accurate numerical analytic models that have been tuned against numerical simulations. For example, the effective tidal one-body formalism is able to predict the gravitational wave phase all the way up to merger within the uncertainties of the numerical results. For most equation of state, here is the result from Bernoulli and collaborators focusing on the SLY equation of state and looking at the binary neutron star with individual components having 1.35 solar masses. So I wouldn't say that the Inspiral is a solved problem. It is not. There are still things that we need to look at. One is the effect of spin. But compared to the post-merger evolution, it's is a subfield where many things have been understood. It's relatively well understood. And in the future, more accurate simulations will be able to tune even more precise analytic models, with which we will really be able to pin down the tidal deformability of neutron stars. So let me switch now to the post-merger evolution. The merger of two neutron stars conventionally ends when the gravitational wave amplitude reaches a maximum. This is roughly at the point where the two neutron stars start to interact strongly with each other. So they have reached contact and they are shearing against each other at this point. After the merger, the typical outcome is that you're going to form an object called hypermassive neutron star, which is going to be supporting and is collapsed by the large degree of differential rotation. So this is what we think is going to be the typical outcome given the constraints on the equation of state we know of. So for example, the fact that the equation of state has to support at least 2 solar masses for a non-rotating model. And given the distribution of masses for neutron stars in binaries, which is strongly peaked around 1.35 solar masses. This hypermassive neutron star has large quadrupolar deformations. It shocks, for example, the accretion torus as it rotates. It emits gravitational waves, and it loses angular momentum, both because of these hydrodynamical processes and probably more important because it emits gravitational waves. So eventually it collapses to a black hole. This can happen within few milliseconds or over time scales of hundreds of milliseconds or even more, depending on the equation of state and initial masses. But this is basically the standard outcome. We have recently started to look very carefully at the evolution of the hypermassive neutron star in its first 10 or 20 milliseconds of life by performing a large number of simulations with tabulated composition and temperature dependent equation of state. This is the largest set to date of this kind of simulation in full GR, and we found some interesting surprises. So here is I'm showing the maximum density as a function of time. The time is shifted so that 0 is the time of merger. And at the bottom, you can see the gravitational wave luminosity. So if you focus on the density, you will see that, of course, as you would expect, when you choose a softer equation of state, you will have higher densities. The merger will be more violent because the neutron stars are more compact. They penetrate deeper in the gravitational potential. They shock very violently, and the post-merger evolution has very wild oscillations before eventually you form black holes, like, for example, for this particular model, the SFHO 135. With stiffer equation of state, the merger is softer. The stars are more tidally deformed, but the encounter is much more gentle. There are not very strong shocks, and the hypermassive neutron star remains stable over the entire time of our simulation. But the interesting thing is in the gravitational wave luminosity. So if you look, there is an initial phase, this is called junk radiation, where the initial data just settles from the initial condition to the evolution. I can explain a little bit better what it is if somebody's interested, but it's really technical. The gravitational wave luminosity grows, it reaches a peak of around 10 to the 56 ergs per second, and then it drops really quickly. So if you look at models, for example, the SFHO 135, the gravitational wave luminosity stays almost constant for 5 milliseconds, and then it drops because you form a black hole. But even for long-lived remnants, the gravitational wave luminosity drops over a time scale of roughly 10 milliseconds or so. So what this is suggesting is that the evolution of the hypermassive neutron star has at least 2 different time scales. There is a very fast time scale where you emit gravitational wave. And then there is going to be a longer time scale where magnetoturbulence effects and thermal effects and other effects that are not completely well simulated in these simulations will play a role. But the gravitational wave emission is so fast that we don't think that anything will be able to interfere with it. So the initial stage for the hypermassive neutron star at 20 milliseconds is entirely dominated by gravitational waves. And you can see this also very well if you look at the evolution of binaries in this kind of diagram. Here I'm showing the total emitted gravitational wave normalized by the mass and the symmetric mass ratio as a function of the angular momentum. So you can think that a binary starts at infinite separation, so infinite angular momentum somewhere up here, and at zero binding energy. So this is a marginally bound system at infinite separation. As the binary evolves, the two neutron stars approach each other, you emit gravitational wave. This energy is lost and goes into binding energy that becomes more and more negative, and you follow a curve like this. At a certain point, the two neutron stars merge, and these are these diamonds. And afterwards, you can notice two things. First of all, the evolution proceeds almost on a straight line. And the reason is that the ratio between energy and angular momentum is, of course, a frequency. So this suggests that the post-merger evolution has a characteristic frequency, which is an eigenfrequency of the hypermassive neutron star. And secondly, if you look at how much the binary loses in energy and angular momentum after 5 milliseconds, these squares, after 10 or 20 and so on, these circles, you see that it loses most of its energy within 10 milliseconds, and that the energy it emits in 10 milliseconds after merger is a factor of a few larger than the entire energy it emitted during the whole Inspiral. So over the whole Inspiral, it emits about 4% of its energy. And then in the last 10 milliseconds, it emits a factor 2 or more. This is a really violent process. And we can also understand why this is the case. The reason is highlighted a little bit in this figure where I show temperature and density for one of these mergers. This is the equal mass 1.35 solar masses evolved with the Latimer-Sweast equation of state. And you find that at the time of the merger is that this time when the two neutron stars are rubbing against each other, then you form a structure which has two cores. This is a very efficient emitter of gravitational wave. On very fast time scale, this loses its angular momentum, and you form something that's more axisymmetric after 10 milliseconds. And the gravitational wave emission at that point becomes lower. And from this point on, we think that other processes like MHD processes that are not included in this simulation start to become important. Another thing that you can notice is that this hypermassive neutron star is relatively cold. The core of the hypermassive neutron star is around 10 MeV, and the density is around 2 times 10 to the 15. So at these densities, the temperature are basically zero temperature, because 10 MeV is really negligible for these densities. The temperature reaches a maximum of about 40 MeV at densities around 5 times 10 to the 14. But we basically find that the thermal support to the hypermassive neutron star is negligible. This confirms also previous results by Kaplan and collaborators. Most of the support actually comes from rotation. As I mentioned briefly before, the post-merger evolution has a characteristic frequency. So the gravitational wave spectrum of the post-merger, which is shown here in this figure I took from this recent work, has a characteristic frequency which has an imprint of the equation of state and on the properties of the binary, and also a number of other features which have been discussed quite a bit in the literature in the past few years, since they were first discovered by Bauswein and collaborators in 2013. But basically, the main thing that people have found is that if you correlate any of these features, like for example this frequency peak, the F2 frequency, or this F1 frequency, which is basically the frequency of the gravitational wave at the time of merger, all of this quantity correlate very well with properties of the equation of state, as is shown in this plot that I took from this paper by Sebastiano Bernuzzi. Here he shows one of these frequencies, this is the dominant one, the F2, as a function of the tidal parameter of the binary. This is basically a combination of the tidal love numbers of the two neutron stars. And what he finds is that independently of the mass, the equation of state, the mass ratio, and some detail on how he treated the thermal component in these simulations that I used to call the equation of state, there is basically a universal relation between this peak frequency and the tidal love numbers of the two neutron stars. So if we are able to measure these frequencies, we would be able to place constraint on the tidal deformability of neutron stars. Unfortunately, these frequencies typically fall out of the sensitivity band of gravitational wave detectors, so it's a bit unlikely that we will observe them, at least until a third generation gravitational wave detector come online. I think I will skip on this because I'm running out of time. And I will instead switch topic a little bit and talk about the neutron-rich outflows. So if you remember, the movie is shown a little bit before. At the moment of merger, part of this neutron-rich material that composes the neutron star gets ejected. And of course, this has long been speculated to be a possible origin.
David, did you cover your microphone a bit or so? Because you're a bit...
Can you hear me?
Oh, better now. Thanks.
Okay. So let's switch topic a little bit and talk about outflows from neutron star binaries. Okay. So at the time of merger, as I've shown a little bit before, what happens is that...
Are you sure your microphone is not covered or something? That you maybe you have something in front of your computer or so, which covers the microphone?
It's not covered, but I think that maybe, let me check.
Sorry, you're pretty quiet.
Okay. I've lost my voice because I had the flu last
Yeah, maybe if you're closer to your laptop like now, it's a bit better.
Okay.
Okay.
Input volume. Is it better now?
Yes, it is very much better.
Yeah, for some reason my laptop decided to change the volume by itself. Okay. So one of the consequences of these mergers is the dynamical ejection of neutron-rich matter, and this has, of course, two important consequences. First of all, this could be the origin of some of the R process elements we observe in our galaxy. And secondly, as a side product of the R process, you're going to produce also radioactive nuclei, and their decay will power electromagnetic transients that we can observe, or we think we'll be able to observe, and possibly also other counterparts. For example, in the radio band, over long time scales, as this ejecta swaps the interstellar medium, it will do something similar to a supernova remnant and produce radio flares over time scales of months or years. So there is a lot of interest now in trying to accurately model this ejecta from neutron star mergers. We also performed our own simulations, and one of our goals, well, our goals are basically listed here. First of all, we wanted to understand what is the main mechanism driving matter ejection. In Newtonian simulations, people find that most of the ejecta comes from tidal tails, while in GR simulations, there are some indications that suggest that instead shocks at the time of merger are a more important component. So we want to really understand where the ejecta come from. More in general, we want to understand what's their composition, their morphology, what is the impact, for example, of weak reactions or of the choice of the equation of state. And more in general, we want to understand if neutron star merger are contributing to any significant degree to the R process abundances we see in our galaxy. So we perform simulation with my code, Whisky THC. One of the main technical advantages that our code has is that it includes this special treatment for the density floor, so for the treatment for low density material that ensures the conservation of mass. And we found that this is really crucial in order to resolve tidal tails that otherwise can be lost in grid-based codes because they have really low density and low temperatures, and they might just be stopped by this numerical floor that we have to include in our simulations. We also included both neutrino cooling with a very simplified prescription and neutrino heating. Here's an example of one of these mergers. I'm showing a visualization performed by another student in Frankfurt, Luc Bouvard. Here on the bottom, you will see the density on the equatorial plane, the color coded. On the back, here you will see the electron fraction or the proton fraction. And here you will see the internal energy of the material on the meridional planes. So I let this binary evolve. This is the same binary that I've shown before in 3D. You see that at the beginning there is a little bit of numerical wind, but this is really at low temperature, low density. It's basically negligible. When the two neutron stars touch, they launch a tidal tail and a more isotropic component, which comes from the shocks. And eventually this binary collapses to a black hole surrounded by an accretion torus. So we can look more carefully at the nature of these outflows, and we identified 3 different mechanisms that drive the ejection. And these are shown here. Here I show density and proton fraction on the meridional plane for this binary. And we identified 3 components. There is a component here at relatively low density, which is very neutron rich. This is the tidal tail. This is the first component that is launched shortly before merger. When the 2 neutron stars approach each other, the acceleration unbinds a part of the tail of the neutron stars. After they come into contact, a second ejection takes place because of the formation of shocks. This material is more isotropically distributed. It reaches up to 60 degrees from the equatorial plane. It comes later, but it's also faster. So there is, you form even a shock between the tidal tail and this material. Since this is shock-heated material, it undergoes a bit of weak reprocessing because of the absorption of positrons onto neutrons. So the proton fraction becomes a bit higher. In our case, we find proton fractions around 0.15 or so. And finally, at high latitudes, we find a very low density neutrino-driven wind with proton fractions of above 0.3, around 0.35. And this is a component that disappears if you turn off neutrino heating. We can look at a bit more systematically at the composition of the ejecta. And here I show on the left side a histogram with the properties of the ejecta from these simulations. We performed 3 different simulations, the same binary. In one case, we switched off all of the weak reactions, so the proton fraction is just passively affected with the fluid, and you don't find anything interesting, so the ejecta have pure neutron star matter composition. In the other 2 simulations, in one, this red one, we included pair processes and neutrino emission, but we didn't include neutrino absorption. What you find is that the matter that's ejected automatically splits into 2 subpopulations, if you want. There is one component at very low weight, this is the tidal tail, and one component at higher weight. This is the shocked ejecta. Once we switch on neutrino heating, this component is reprocessed to higher proton fractions, and you also form this tail at large weight. We're also able, with a student here at Caltech, Jonas Liebner, to compute our process abundances from this ejecta. And we find 2 things. First of all, we find that at high atomic mass number, A, above around 120, we find an almost universal pattern. And the reason is, of course, that even when we include neutrino heating in all of our simulations, most of the ejecta has proton fraction of less than 0.25. So most of this material undergoes fission cycling, and you get this universal pattern that agrees quite well with the solar abundances. And we find much larger deviations between these different models at lower atomic mass numbers and around the first peak of their process elements, where neutrino play a very important role. However, in none of our simulations we are able to completely explain solar abundances around this low A nuclei, relatively low A nuclei. So if our results were to hold, this would suggest that either you need contribution from, for example, winds coming out later from the binaries or from core collapse supernovae in order to explain the abundances we see in our solar system today. We also performed a similar study where we looked at the effects of different equational state. Here are 3 different binaries having the same mass. And in this case, we didn't include neutrino heating. And we find a similar picture. So all of the ejecta without neutrino heating, at least, are relatively neutron rich, and you robustly form second and third R-peak elements, and we have troubles explaining the first peak element. However, what I would like to stress here is that these results are not that satisfactory from the point of view of the total ejection of mass. So we think that we have we recover a very robust pattern at high atomic mass numbers, but if we were to estimate the total contribution of neutron star binaries to the production of these elements, I think we'll still be in trouble in a sense, because we find results that vary by a factor of 5 between different groups. For example, for the SFHO binary, our simulations find around 2 times 10 to the minus 3 solar masses of ejecta, while other simulations find almost a factor of 5 larger. And these simulations have very similar microphysics and hydrodynamical evolution schemes. So what we think that it is happening here is that these ejecta are probably still under-resolved, and the hydrodynamics is not entirely under control. So in order to be able to really make a statement about how important neutron star mergers are at producing these elements, the key point now is getting the hydrodynamics right, more than probably getting the composition right. So here are my conclusions. So we have talked a little bit about the Inspiral. The Inspiral phase of neutron star mergers is relatively well understood, and tidal effects are really promising to constrain the neutron star equation of state. We think that after a few years of detections with advanced LIGO at its design sensitivity after 2019, we'll be able to constrain the radius of neutron star to less than ½ kilometer or so. The early burst merge is also starting to be understood. We have understood that there are 2 time scales involved, and the first part of the evolution is dominated by gravitational waves and hydrodynamics in the hypermassive neutron star, which are relatively under control. And over longer time scales, we have magnetoturbulence effects that are either not included or not resolved in present simulations. So what happens after 10 or 20 milliseconds is still to be completely understood, and there is the work connection with gamma ray burst, for example, that I didn't talk about, that needs to be understood. But at least the early post-merge is now being understood. From the point of view of nucleosynthesis and the ejecta, there is still also a lot of work to do. We have to include MHD. We have to have better hydrodynamical models that agree between different groups. We have to do much better with radiation. I've shown that the first peak abundances have a sensitivity on neutrino radiation, which is not treated very accurately in any simulation. And I didn't talk about it, but another important aspect is that after the dynamical ejecta is launched, there is going to be a secular ejection of matter from the remnant accretion disk, which also needs to be included self-consistently. Finally, I was asked to include a wish list, if you want, or things that would be helpful to have from other people in the JINA collaboration. And among these, of course, are equational state tables, observational data against which to compare. But most importantly, I would say is actually feedback. It's actually having you asking questions to me, because I do simulations in the hope that this will be useful for people that do nuclear astrophysics. So this is everything I want to say. Thank you.
Okay, thank you very much for this great talk. If you have questions, then please indicate so in the chat. and then I will call you. Okay, then MSU can start.
Okay.
Hi, David. That was a nice talk. If you want to extract the equation of state from Tidal deformability, usually at some point you have to need like a template waveform. At some point you have to match this on to the very early part of the Inspiral. And I guess the question is that all under control that one can do this?
Yes, actually, for the tidal, for measuring tidal effects, what is going to happen is that only analytical that have been tuned against the light. The reason is this parameter estimates gravitational wave need to be able to produce of the order of or more in order to in Monte Carlo. And this would be impossible with numerical relativity simulation. What we actually want to use numerical relativity as a way to calibrate. Then we
Use the microphone and there's a feedback.
David, can you repeat that last part? You were going in and out of volume.
Okay, I'm sorry about that. From the point of view of doing parameter estimation, what we really want to have at the end is an analytic model that spans all the frequency range all the way to merger. We don't want to do this hybridization anymore, this matching between numerical and analytic predictions. We want to have a model that can cover everything. And current analytic models do a very good job until the last cycle, basically, when the neutron stars are already in contact. Improving on that will require higher resolution simulations. But the way forward is to use only analytic models that have been calibrated against numerical relativity simulations.
Okay, Sanjay had a question.
Hi, David. First, let me just say that I really enjoyed your talk. It's one of the clearest talks on the subject that I've heard. My question to you is there any effort to model the electromagnetic emission from all the ejecta that you're getting, not just things that might look like kilonova, but this matter that is being thrown out is probably being bombarded by neutrinos. What is the ongoing effort to understand electromagnetic emission after merger?
So there are efforts that are more concerned with MHD effects, and there are efforts that are more concerned with just the ejection of matter. So yeah, I would say that the current state of the art is we know how to produce light curves from this dynamical ejecta. We know how to produce, or we think we know how to estimate the kind of electromagnetic counterpart that you will get from, for example, disk wind ejecta on longer time scales. And what really remains to be done is putting everything together and have a self-consistent model that includes both the evolution of the remnant disk, the way in which the wind from this disk interacts with the ejecta, and the final electromagnetic signature. And all of this even without including MHD. When you throw in MHD, a lot of other things happen, and there are a lot of possible ways to produce electromagnetic counterparts, some of these more speculative than others. And of course, there the main goal is understanding if neutron star binaries can produce short gamma ray bursts. But there is a wide range of possible things that can happen. And
so maybe I can just follow up. So the mechanism for short gamma ray bursts and very specific emissions from kilonova may require a lot of modeling, but are there any more, simpler, more robust electromagnetic signatures, either in the gamma rays or in the X-rays, that you can predict based on just the material ejecting and the fact that this material is hot and being acted upon by a very intense neutrino spectrum?
Yeah, I would say that the predictions we have for kilonova are robust in the sense that you can predict the main features of the kilonova emission by knowing the composition and using models that are basically similar to shock breakout models in supernovae. The main uncertainty there is probably the opacity of these heavy elements that you're going to produce. But I think that, well, I wouldn't say it's under control. There has been a lot of work in that direction.
Okay, thank you.
Okay, Chuck had a question?
Nice talk. So my question is about ejecta mass, how it depends on the mass ratio and on the equation of state.
So the dependence on the equation of state is that softer equation of state have larger ejecta mass. This is a bit counterintuitive if you think of Newtonian simulations, because there, if you have a soft equation of state, you have less tidal ejecta. But actually, most of the ejecta in GR simulation comes from shocks. And when you have soft equation of state, you have small neutron stars, they penetrate deeper in the potential, so they have stronger shocks. If you have large mass asymmetries, you can produce more ejecta in the form of tidal tails. So large mass asymmetries also drive larger ejecta. So in general, soft equation of state, large mass asymmetries are good for producing a lot of ejecta. You can produce probably around 1% of a solar mass. Stiff equation of state and equal mass binaries are a bit less optimistic in the total amount of ejecta mass.
Okay, is there any other question? One more. Okay, Sanjay.
So, this is relating to what you just said about shock ejecta. Is it sensitive to the temperature achieved in the neutron star? I mean, is it thermally ejected material so that you take a shock and convert and use this to eject it?
Sorry, I missed the last sentence that you said.
So I understand that softer equations of state, you have more energy in the shocks, but is the ejecta sensitive to the temperature?
Okay, the question that I understood is the ejecta mass sensitive to the temperature? I would think so. I wouldn't know exactly how to test this with numerical simulations. As I said, however, I don't think that any of these GR simulations are currently well resolved enough to really pinpoint exact numbers in the ejection mass. There is at least an uncertainty of a factor of 2 or more. Yes, in general, it's really, as you said, softer equation of state, they produce stronger shocks, higher temperatures, and eject more matter.
So, but you could produce a higher temperature by also having, changes to the specific heat. You said that the temperature was, a few times 10 to the 14. So I'm just, for the first time I'm thinking about this and wondering whether specific heat of matter around nuclear density could actually have some role to play in amount of ejecta.
It is possible. It would be something interesting to test with numerical simulations. But I don't have a way to reply at the moment with the current data that I have.
Well, maybe we should talk offline about trying equations of state with very different specific heats.
Yeah, that would be something interesting. This is the kind of feedback that I would like to have.
Okay.
Just wanted to follow up on the discussion of the temperature. Is the temperature of the low density matter that's ejected, is that really resolved, or are there still numerical issues in determining the temperature of the ejecta?
Well, the temperature, I think, is relatively well resolved in the tidal tail. The tidal tail is really cold, but if you look at the density profile, it's really smooth. So it's relatively well resolved. Of course, the problem comes from the fact that as the ejecta moves out, the equation of state that we use is NSE, and the ejecta will go out of NSE, so everything becomes unphysical. But apart from this issue, at least at small radii, I think that the temperature is relatively well resolved in the tidal tails. The temperature in the shocked ejecta might actually change if we include, for example, magnetic fields, because part of this thermal energy comes from shearing. And when you include magnetic fields, this is another channel where you can put this energy at the time of merger. But I don't think anybody has really looked at this with simulations that are sufficiently resolved to say whether magnetic fields change the amount of shocked ejecta in this way.
Okay. Are there any more questions? Otherwise, I would like to thank you again for this great talk. And yeah, see you all. I hope I see you all for the next GINA seminar, and goodbye.